Welcome. This is video number 301. In this video, I am going to estimate the Lin-Log model to verify the famous Engel curve. Now, Engel curve means that total food expenditure increases with the total income, but at a decreasing rate. So, let me start with the introduction of the Lin-Log model. Unlike the growth model that we discussed in our video number 298, in which we were interested in finding the percent growth in the dependent variable y for n absolute change in x, suppose we now want to find out the absolute change in y for a percentage change in x. A model that can accomplish this purpose can be written as follows. Yt is equal to a plus b natural log of xt plus ut. Model of this kind is called a Lin-Log model. As usual, the slope coefficient b is equal to change in y divided by change in x, or b is equal to delta y over delta x. In Lin-Log model, beta or b is equal to absolute change in y, that is delta y, divided by relative change in x. The second step follows from the fact that a change in the log of a number is a relative change. So symbolically, we have b is equal to delta y divided by delta x or x, or delta y is equal to the slope coefficient times relative change in x, and that is delta x or delta change x, delta x over x. Delta y is equal to the slope coefficient beta or b times delta x over x states that absolute change in y equals the slope coefficient b times the relative change in x variable. If the latter is multiplied by 100, then the above equation gives us the absolute change in y for a percentage change in x. Thus, if delta x divided by x changes by 0.01 unit or 1%, the absolute change in y is 0.01 times slope coefficient. If in n application we find that b is equal to 500, the absolute change in y is 0.01 times 500, and that is equal to 5. Therefore, when regression of the Lin-Log is estimated by OLS, do not forget to multiply the value of the estimated coefficient, the slope coefficient, by 0.01, or what amounts to the same thing, divide it by 100. If you do not keep this in mind, your interpretation in any application will be highly misleading. The practical question is, when a Lin-Log model like the above is useful. An interesting application has been found in microeconomic theory, which is the so-called Engel Expenditure Model, which is named after the German statistician Ernst Engel. Engel postulated that total expenditure that is devoted to food tends to increase in arithmetic progression as total expenditure increases in geometric progression. In order to prove this, I will use some hypothetical example in my stata, and I have already opened my file. Let me show you these variables. Here I have one variable as food expenditure, and this is a total expenditure. These are the residual that I estimated, and this is the date variable. That is, this time series data is quarterly. This is the trend, and finally, this is the natural log of total expenditure. Since I'm going to estimate the Lin-Log model, so I will regress finally food expenditure in linear form on the natural log of total expenditure. Before I do that, let me first show you the data. Here are the various variables. These are serial numbers, these are food expenditure, these are total expenditure, these are residuals, this is data, and it starts from 1993 quarter 1 up to 1998 quarter 3. And this is trend variable, time variable, and this is natural log of total expenditure. And if you take the natural log of 382, that will be equal to 5.945421. So this, if you take the natural log of this column, we get this column of natural log. So let me minimize this, and here I can regress food expenditure. This is my food expenditure variable, and I will regress this on total natural log of total expenditure, and here are my regression results. Now, as usual, this is the regression sum of square, or explained sum of square. We also call this model sum of square, and this is the unexplained sum of square, or residual sum of square, and this is the total sum of square. These are degrees of freedoms, and here we see this is our f state value, which is equal to 32. Total number of observation, these are equal to 55. This is the p value of the f statistic. This is the r squared value. This is adjusted r square value. This is the coefficient of the intercept term, and that is minus. Usually the constant terms doesn't have any economic meaning, and this is the 2922 is the standard error of the constant term. This is the t value of the constant term. Since the algebraic sign of this constant is negative, and this negative term divided by this will be equal to minus. So the algebraic sign of the coefficient and its t value go side by side. This is the coefficient of the natural log of total expenditure, and this is its standard error, and this is the t state for natural log of total expenditure. These are the p values. So these p values show that these two coefficients are highly significant. So let me show you the graph of food expenditure and total expenditure, and I'll show its scatter. So I'll go to graph and 2A graph, and in 2A graph I want to go to create, and yes, so my y variable should be natural log of total expenditure. Sorry, it should be like this, and here is the total natural log of total expenditure, and my x variable should be food expenditure, and I'll say okay. So plot, yes, this shows that total expenditure increases, that food expenditure increases with total expenditure or with total income, but at a decreasing rate. So this kind of model can be estimated with the help of Lin-Log model. So that is why the Engel curve is estimated or can be estimated with the help of Lin-Log model. So ladies and gentlemen,